aspect of this, and they're pretty good at explaining what an integral is doing and what the fundamental theorem of calculus is. Okay, so first of all, we're going to look at the example. You have a daily cost function given by this function here. Okay, c of x equals 180x plus 200 from 0 to 20. Okay, can you tell me what the marginal cost is?
180.
180. What does the marginal cost mean? It means take the derivative or get a rate of change of the cost. So yeah, that derivative of 180x plus 200 is 180. C of x is a line. Its slope or its rate of change is 180. Okay, so we have that. Now the next question is, what is the change in cost as the production goes from 5 to 10? Well, what you're going to do first of all is you're really going to do C of 5. Okay, so you want to just plug that 5 into the function. So that's 180 times 5 plus 200. Okay, so let's go ahead and get that worked out. So 180 times 5 and then plus 200. I'm just going to do it on the calculator. That's given 1100. Okay, then I'm going to go ahead and do the same thing with C of 10. The cost is changing and it's increasing basically as we do more and more items. So we're going to do 180 times 10 and then plus 200. Okay, so if we do that, that would just be 1800 plus 200. That should be 2000. Okay, so we have that. Now, what do you do with those two numbers? You're finding the change, so what do? You subtract them. Okay, exactly. So what you're going to do is you're going to do C of 10 minus C of 5. Okay, and we're going to do it in that order. So we're going to have 2000 minus 1100, which is going to give, you have a change of 900. And this is in dollars, it says in the problem. So that's the change in cost. Okay, it's just the difference between the two. Okay, so what I'm going to show you is the graphs. The graphs were kind of nice, so I just copied these out of the book. So what I have here in this graph is I have the graph of the cost function. And that's a line, okay? It's got a y-intercept of 200, okay? Then it's sloping upwards by 180. And then what we just found was that change in cost like that. So we're looking at this function value there and that function value there. That's the change in cost, is that what we just did. Now, what I did also is the marginal cost is 180. So I also graphed the marginal cost. Does that make sense? It's a constant, so it's a straight line this way. Okay, now what I want you to notice on there is the area is what we're trying to establish when we're working out these integrals is this. So it turns out if you look at this area on this right here, if you look at this, what you're going to get is what's the base of this rectangle? It's 5, right? What's the height of this rectangle? Well, it's going to be that 900 that we, or not the 900, I'm sorry, it's going to be 180. Okay, why is it 180? Because the line is up 180, right? Now, if you find the area, you're just doing base times height. So the base is 5, and then the height is going to be 180. So notice it also gives 900. So it turns out the connection that you're trying to make, this is kind of a nice way to explain this, but I think the book did a good job of doing this, is if you're doing an integral, if you were going to do the integral of this, what you would end up doing is you would go from 5 to 10, and then the antiderivative. The antiderivative would be over here. Okay, so what you're doing, if you're going to do the integral of that thing from 5 to 10, you're going to end up getting that area under the curve. That's what we're learning what that is, and that's how it relates to that. So when you do that antiderivative, you go back here, but the value of that definite integral is going to be that. So actually what you would do is if you, and you want to write this down, if you do the integral of 180 dx from 5 to 10, you're going to end up getting 900. Okay, that's what you'll end up getting when you do that. Now, once we learn how to do that, that I think will make a lot of sense to you. So the connection between the changing cost and the area under curve or marginal cost is they're the same. Okay, does that look okay? That's pretty easy to see the areas are the same by doing that, but this is sort of trying to help you understand what an integral is going to do. Okay? Okay, I'm going to do another example that kind of has that, where we're going to put the whole thing together mostly ourselves. So let's just go to the next page. I think on this one I just took this example from the book, and we'll do the parts on the next page here, okay? All right, so let's go ahead and do a graph. And we want to use our calculator on this, so let's go ahead and put the function in that I gave you in your calculator. This will be a parabola, and we want to get a nice accurate graph on this. So let's put in the function is negative 5x to the second plus 210x. And then we're going to have to figure out a good viewing window on this, and then plus 400. Okay, so we got that put in. Now let's think about the window. All right, if you read the problem, what would be a good way to scale the x? I mean, what's x going to go from? 0 to 20. I gave that to you. Now, generally, that's something that's kind of the domain of that function. So let's go 0 to 20. And scale by whatever if you want to. I think what I'm going to do is just scale by 5. You can scale by 1 if you want to, like that. And then the other thing on this problem is you've got to figure out y. Now, what is the significance of that number 400? I think that's real important to know.
Y-axis.
That's the y-intercept, right? Because if you let x be 0, you get 400. So this graph is going to start up at 400. Okay, so let's try like this. Let's go 0... On the y, let's go 0 to 400, like that. And then maybe we could scale that by 100 or 50 or something like that. Let's just scale that by 100, like that. Okay, and I'll slide this over here. And let's start by trying that viewing window. And you should have a parabola that's going upside down. Where is my parabola? Is your parabola okay?
Yeah.
Let's
go bigger than 4.
Probably do. Okay, well, let's go through and let's look at.
Table values has about 3,000.
Yeah, it's like 3,000.
That's weird. Maybe it goes up and then goes down again. I guess that's what it does. Yeah, let's go up. Anybody try anything different?
I started at 400 from my minimum.
0 to what?
I did 400 to 3,000.
Oh, okay. Well, let's start at 0, and let's take your advice and let's go 3,000. I think what it does is it starts at 400, it goes up, and then it goes down again. And sometimes on the Y window, you got to play with it a little bit. Let's try this. Where is my parabola? What did I do? Okay, oops. Okay, my eyesight. Okay, those of you who have got this done, are you seeing a parabola? Okay. Okay, let's see if that's a good viewing window. We want to kind of see where that maximum is on that too. Let's see now. Hallelujah. I think I finally got it. Okay, so let's use that viewing window, so that should be good. All right, and let's just go ahead and kind of get a scale on here then. So let's kind of go like something like this. Let's go 1, 2, 3, 4, 5. Let's just kind of scale like this. 5, 6, 7, 8, 9, 10, 11, 12, 13. And I may be wrong because my eyes are not good. 16, 17, 18, 19, 20. Okay, like that. All right, that'll be our x-axis. And then just do 1,000. We can kind of pick this in different ways. We could go, I would probably just go like every 5 is 1,000 or something like that. 1, 2, 3, 4, 5. That's 1,000. 1, 2, 3, 4, 5. That's 2,000, and so forth. Okay, and then generally, you know, when you're doing a graph like this, you want to label stuff like that. Your graph is nonsense if you don't label stuff like that. Cost, X, you can just put X there. That's the number of units. I don't think I tell you what this is on the problem. It just says units. Okay, so this would just be C, or the number of units. Now, really what I'd want you to do on this problem is just get maybe like 3 or 4 good points by tracing. Okay, so a good starting point is to trace at 0. And if you trace at 0, you're going to get 400. I knew that was going to come up. So I'm really going 2, 4, 6, 8. So my 400 would be right there. Okay, and then just pick another one. Let's go to the end. At the end, we could trace at 20 and get that value. Okay, and that's 2,600. So that would kind of go like 22, 24, 26. So it would kind of go over like that. And if you label a couple of points, you don't have to do that, but I like students to do that. And then really from there, you can get another point if you want to, anywhere you want to. Let's go 10. And I think that's probably good enough for a sketch. So if I trace it 10, that'll give 2,000. So that's a good pick. And I'm going to write that as 10, 2,000. Now see, this is a good graph. That's what graphs should look like. You should have points, everything labeled. That's what I expect students to do for a graph. Okay? And I expect you to use your graphing calculator. I'm not going to have you do that any other way. Okay, so what we're going to do now is we're going to work with the marginal function then. Okay? So first of all, I gave you the cost function on here. So c of x is negative 5x squared plus 210x plus 400. So what do you do to find the marginal cost function? Take the derivative. So what is that?
Negative 10x plus 210.
There you go. Negative 10x plus 210. Okay? Now let's use our calculator on that. Even though it's a line, let's go ahead and just do a graph on that also. Okay, so let's put that in and get a kind of a nice accurate graph. All you need on a line is 2 points. We have a y-intercept already, so we're going to put in negative 10x plus 210. Same scale. Now the scale on the y may be way off on this. I mean, it would be way off. So you see, I get a line going like that. That's not a very good scale. So see, what's happening is the y-intercept is 10 and the slope's negative. So does that make sense that 210 is as big as we need to be? And we're going down. So let's do the window on this like this. Let's just go like, let's 0 to 20 on x is the same. Let's go maybe 0 to 250. This is just my thought. And then scale by 50. Okay, and I'll slide that over there so you can see that. You can put it in this way if you want to, or if you have a different idea, that's good. Now see, all I need to do on this when I draw this graph is get my scale and then just get 2 points. Okay, so I'm going to go the same way I did on the last one. I'm just going to go every 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20 like that. And then we're going by 50s. We were going all the way up. Let's see, we could do this in lots of different ways. We could go like 50, every 2 is 50 or something like that, whatever you want to do. 150, 200, 250, and so forth like that. You can do that or something a little different if you want to. And all we're doing is getting a sketch, a good enough sketch. So I'm going to trace it 2 points. So if I trace it 0, you should already know that. That's the y-intercept. So that's 210. So I'm just going to kind of estimate where that is, put a dot there, and label that as 0, 2, 10. The next logical thing to do would just plug in 20. So if you trace 20, you're going to get 10. So I'm going to just estimate that point as 2010. Okay, like that. And then you can sketch that line together like that. And then that would be, you would want to label this as marginal cost. And then you can label that as x, like that. Okay, so what I'm trying to show you with this problem is the idea of what an integral does and what the area under a curve does. So what we're going to do with this then is it says you want to calculate the area under the curve from 5 to 10. Okay, so the first thing that we want to do on this is go ahead and we want to look at this. We're going to go ahead up on this graph and we're going to do C of 10 minus C of 5. Okay, what we're going to do is just look at the change in cost from 10 to 5. Okay, and again, you can do this. We already got that. Okay, I guess I probably should have traced it 5. So we already have that C of 10 is 2,000. Okay, and if you do C of 5,
1325.
what do you get?
1325.
Thank you, 1325. Now the way you can get that is just by plugging into the cost function, or go back and graph that and trace out like that. Okay, so if you do 2,000 minus 1325, you're going to get a change of $675. Okay, All right, does everybody understand where that's coming from? Okay, just getting y values for the cost. All right. Now what we're going to do is we're going to do an area. So on this one, what we're going to do is we're going to do the area from 5 to 10. So you want to just draw kind of a little diagram on here like this. Okay, then that is going to be the area that we're going to consider right there. Okay, so we're going to find that area. What kind of shape is that? It's trapezoid. Okay, so good. So the area of this trapezoid is going to end up being base times height over 2. Okay, now that's triangle. Okay, that's the one that goes 1/2 height times the sum of the two bases. Okay, so the bases are these two things. This base right here would be, you'd have to figure out what C prime of 5 is. And then this base here, you'd have to figure out what that is. And then the height is going to be equal to 5 like that. Now I got my calculator graphed on this, so it's wise to just go ahead and trace on these things. So if you traced it 5, you're just finding C prime of 5. That gives you 160. So I'm going to label this point here as 5, 160. Then I'm going to trace it 10. And I'm going to label this point as 10, 110 like that. Okay? Now I've got all the information I need on this problem. Okay, so what is the height of the trapezoid? 5. What are the bases?
160.
Yeah, they're these numbers right here. It's just how those bases are that long. Okay, so what we're going to do is we're just going to do 160 plus 110. Okay, and do that then. Okay, so you can do this on your calculator if you want to. That's 1/2 times 5. I'm going to put that over 1. If I add what's in the parentheses on that, I'm going to end up getting, let's see, what is that, 270? Okay. All right, then we can do that. You could actually just multiply straight across on that. If you do 5 times 270, this is one way to do that. You get 1350 all over 2. Okay, we do that. We got the same answer, 675. That's what I wanted you to see. Okay, so the answer to C is they are the same. Okay, that's the idea. Okay, so that's really what's going to happen. There's one other thing I want you to write on your paper, because what we're going to get to here is what the meaning of this problem right here is you're really doing the integral of the marginal cost, negative 10x plus 210, and you're doing that from 5 to 10. Okay, and we're going to learn the second half of class actually how to do that. Okay, all right, does that make sense, what we did on the problem? Okay, that's a pretty good way, I think, to introduce students to the idea. Okay, so let's go ahead and do a 10-minute break here, and then we'll come back and then we'll work on how to do definite integrals. Okay, so this tells you what definite integrals are and how you work them out. So I'll go through enough that'll help you understand this. So if you're doing a definite integral, turns out what you do is you do the antiderivative. Remember, the capital F stands for the antiderivative. And then what you do is you evaluate the upper limit, you evaluate the lower limit, and then you subtract. Now, one thing that'll kind of help you a little bit on that, I think, is some basic examples will kind of get you going on that. I think that'll help you understand why this works the way it does. Okay, I'm going to show you in this example 3 how this works. Okay, so first of all, this is a real good starting example. So what we're going to do is I want you to graph y equals 5. Well, how do you graph y equals 5? It's a horizontal line, okay? It goes like this. So you want to go ahead and just graph out a line like this, straight across through 5 like that. And the mathematical meaning of this problem is, since you're going from 2 to 8, you're finding the area under the curve. So we want to go in our diagram, you want to just kind of go up through 2 all the way to 8. And then you want to shade in that region right there. Now we're going to do it 2 ways. We're going to do just the formula, and then we're going to do the fundamental theorem to find that area. So that's the region. When we're doing this integral, that's what you're doing, is you're finding that area. Okay? What kind of shape is this? It's a rectangle. Or is it a square? Well, a square is a special rectangle. Okay, I see 4 sides with 4 right angles, so it's a rectangle. What's the formula for an area of a rectangle? Base times height. Okay, so what we need to do on this then is, let's see, it looks like the base would just be, the distance from 8 to 2 would be 6. Okay, the height is what? 5, okay, so we got that. So the area is 6 times 5, so it's going to be 30. Okay, that's how you would find the area. Now what we're going to do is we're now going to do the integral. I'm now going to show you how this integral works. Okay, what you guys know how to do so far is how to do antiderivatives. Okay, so what would be a function you take a derivative of that would give you 5x? Or no, 5. I just told you the answer. Okay, 5x. Okay, so the antiderivative is 5x. Now, you're used to putting a plus c. You don't put a plus c on a definite integral. What you do is you usually put a bar and then you put 2 to 8. That's just the notational thing we're going to do. And then when you do the fundamental theorem, here's what you do. You just take and plug this in. First of all, you're going to go 5 times 8, like that. Then you're going to go 5 times 2, like that. And then you're going to subtract the result. Okay, and that should give us the same answer, 30. Let's see if it does. That's 40 minus 10. So indeed, the net area is 30. That's how it works. Okay, that's how you actually do a definite integral. Now, I want to try to help you understand what's going on this. Is when you look at this 40, what you're really doing on this, when you're actually doing an integral like this, you're actually doing this. You think about this. You're actually going from 0 to 8. If we did the area from 0 to 8, wouldn't that be 40? Think about that. That distance there, that basis would be 8. The height's 5. So that whole area from here to here is 40. The significance of this 10 right here is it's this little piece right here. Isn't this thing going to be 10? 2 times 5? So what you're doing is the whole minus the part to give the rest. That's what you're doing. So that upper limit is kind of giving you 40, then you're doing the 10, and it's left over. That's why we subtract when we do that. Does that make any sense? Okay, so it's just kind of the 40 is the whole, this part's 10. 40 is the whole part like that. That's it. That's how you do that. Okay, let's go to the next page. I think we already did a problem like this on the previous section. So let's go ahead and just graph this out. And then we're going to do the integral on that. We'll be able to do that now. Okay, so it looks like you have a y-intercept of 3. You have a slope of 2. So you want to go ahead and just graph that out. So just go up 2 over 1 until we run out of room. Okay, then we can go ahead and draw the line on that. Okay, and let's see. We're going from 2 to 4. So that means what you want to do on your graph is you want to just go kind of like a dashed line up to 2, a dashed line at 4, like that, and so forth. Okay? So what we have is we have a region like that we want to find the area of. So we've already talked about this same problem. What kind of shape is that? That is a trapezoid. And like we did in the previous section, that area is, the formula is 1/2 height times sum of the bases. So we're going to do it this way, okay, to start with, okay? So if you look at your diagram, the height, and see the height is the distance between the bases. It doesn't mean how tall it is, it's that, so that's 2, okay? The heights right here would be the function value. So this base right here would be 7, okay? And notice if you plugged in 2, you would have 2 times 2 plus 3 is 7, if you just plug that in. And then the height at 4 would be 2 times 4 plus 3, that would be 11. So that base right there is 11, like that, okay? So when you do the calculation, you're going to have 1/2 times the height, which is 2. The bases are 7 and 11, so you do that. 2's cross out, answer is 18. So the area of that trapezoid is 18. Okay, everybody solid with that? Okay, so here's what's new. Now, what we're going to do is we're going to do the integral. We now know how to do this. So we're going to go ahead and do an antiderivative, but then we're going to evaluate it, and we're going to see if we don't get 18 on this. Okay? So the first thing is let's just kind of think about the antiderivative. Now you can break this up like this if you want to. You can say 2x from 2 to 4. You can do it in your head too. Plus the integral of 3 dx from 2 to 4. All you're really doing is the antiderivative of each part. Okay? So let's do this kind of carefully. The 2 is going to come down. How do you do the integral of x to the first? You do the power rule for an integral. It goes up, it's x squared over 2. Remember, you add 1 to the exponent, then divide. That's the power rule for an integral. Okay? That's what we learned. You got to be totally solid on that for your test that you're going to have Thursday. Okay? What's the antiderivative of 3? 3x. Okay? So what I'm doing is I'm doing kind of the antiderivative. The 2's are going to cross out. Okay? Now, just do this real quick. You got to learn how to do this if you're going to learn how to do this the right way. What is the derivative of x squared? Look at that. What's the derivative of 3x? See, we're right. Every time you do an antiderivative, you can tell you're right. Okay? So what we're going to do is go ahead and write down x squared plus 3x. Put your bar there. Usually kind of write it like this. And then we're going to evaluate that from 2 to 4 like that. All right. So that's how the antiderivative goes. Now we do go like this. First thing we do is we plug the 4 in. So we're going to have 4 to the second plus 3 times 4, like that. Okay. Then what you do is you plug the 2 in. So you're going to have 2 to the second plus 3 times 2, and then you subtract the result. And that's what the fundamental theorem is saying. It's just saying evaluate the antiderivative at the upper limit, evaluate at the lower, and then subtract. Okay, we work it out. Let's see if we don't get 18. Okay, so the first parenthesis is going to be 16 plus 12. The second one's going to be 4 plus 6. So it looks like I get, what's that, 28 minus 10. Told you so. Okay, so it's 18. And you can do that on your calculator. I mean, you know now how to kind of do an integral on your calculator. You can verify it that way too. So your net area is 18. So you don't have to graph anymore. Okay, and the reason I've been doing these special shapes is because we have formulas for them. Okay, so is everybody following okay? How I did that integral? That's what we're going to be working on here. Okay, so let's do this next one here. Now, what the thing is on this one is, you don't have any, you've never in your life learned a formula for that kind of a curve. You never have. You never will, okay? The thing is, you don't need to because the integral is going to give that area anyway. You know how to do that integral. So what we're going to do is find the area from 0 to 10. So what we're going to do is just do the calculus now. So, all right, let's go ahead and break this up into 2 integrals. We're going to go 0 to 10, 60x dx, minus the integral 0 to 10 of 6x squared dx. Now this is all about the power rule. I can't tell if everybody knows the power rule. I'm kind of thinking some of you don't. And you want to do that real fast. For example, if you had x to the 10th, what is that?
X 11.
You don't want to waste any time on that. That's the power rule. Exponent goes up 1, divide by the result. Okay? Couple of things you can do on this problem. You don't have to write that first step if you don't want to. You can do the antiderivative in your head if you want to. I can take that out. Okay, so I can write that like this. I can take the 6 out and then go like that. Okay, now you can bypass those 2 steps because you can learn to do that antiderivative in your head anyway. Okay, so what do we have? What is the antiderivative of x to the first? X to the second over 2. All right, power rule for integrals. What's the antiderivative of x to the second? X to the third over 3. Okay, so that's how that goes. Simplify whatever you can. 60 over 2 is 30. You have x to the second. 6 over 3 is 2. So you have x to the third. Okay? It's always good on problems like this. I wish students would kind of do steps and check, because if you're wrong, then you're wasting your time. What's the derivative of 30x squared? 6x. What's the derivative of 2x to the third? See how long that took? It took like 5 seconds of our time to know that we're right. So now what we're going to do is we're going to evaluate that from 0 to 10. Okay? And this is the part, sometimes the arithmetic gets kind of hairy on this. It's probably not too bad on this one. So let's just go ahead and plug in and do 30 times 10 to the second minus 2 times 10 to the third. You can use your calculator to help you, so you plug in the 10. And you're going to love it when I give you a 0, because it makes it so much easier. So you're going to have 30 times 0 to the second minus 2 times 0 to the third. Crunch out the details and you'll have that area. Okay, so that's going to be, and you can do this whole thing in one step on your calculator if you want to. That's really just 30 times 100. That's going to be 3,000. You can even bypass that, and then you got 2 times 1,000. Like that. And then what's the second one?
0.
Yeah, it's just 0, okay? So that kind of helps. So then if you do this, it looks like you just have 1,000 there, because that's 3,000 minus 2,000 minus 0, so it's equal to 1,000. So the rest of the problem when you do that is getting that, region on there that's given the area. You're doing the arithmetic. Okay, so that's exactly what that area is. If you did that and graphed that on your calculator and did this stuff, I went ahead and wrote down what you do on your calculator. You can check that. Now, I want you to do one other thing with this problem, because this mysterious dx, I'm now going to explain what it really is, okay? So what I want you to do on this is just draw out a couple of rectangles with just the idea of left endpoints. We can just do it like that. Now remember, what I showed you in yesterday's class is you can think of an area under a curve as a bunch of rectangles being added. But the more rectangles you have, the more exact your answer is, right? So if we make an infinite number of rectangles there, we'll get the exact answer, okay? The idea is this, okay? This thing right here, the whole key to this is that is f, that's the function value. The height of that rectangle is the function value. The base on this is, we called it delta x in yesterday's class. Now we're going to call it dx. What's the difference? Dx is infinitely small. So the idea is dx represents a base of a rectangle. It's not 0. It's as close to 0 as you can theoretically get. Does that make any sense? That's real abstract, but the more rectangles you have, the smaller the base is going to get. Okay, so what really an integral is doing is it's a limit of all those rectangles as that dx gets smaller and smaller like that. So what you have in an integral, when you have f of x dx, this is a good thing to write down, that is the base, that's the height. Okay, that's what you're doing. Okay, it's base times height. The height is the function value, the base is the dx. That's why it's there. Okay, that's the idea. All right, so it's kind of nice to begin to get an idea of what that dx is doing. Okay, next page, let's crunch out some integrals. I think I want to spend time just kind of going over some of the integrals here. So we're kind of established the area. Now we're just going to work out definite integrals, okay? All right, so a good way to start this one is to take the 9 out. Okay, and then we're going to do the integral of x dx from 0 to 8. Okay, this one's pretty easy. Okay, what is the antiderivative of x the first? X squared over 2. So you're going to have 9 times x squared over 2, and then you're going to evaluate that antiderivative from 0 to 8. So that's how you work that out. The 9 is just separate. You'll just multiply the answer by 9 at the end. Okay, so when we do this, we just bring down the 9, and then we plug in the 8. So we'd have 8 to the second over 2, plug in the 0, so you'd have 0 to the second over 2 like that. So once you get your antiderivative, you always do 2 things. Plug in the upper limit, plug in the lower, and subtract in that order. That goes like that. Now to work this out from here, what we would have is 9 times 64 over 2 minus 0 over 2. So that's just 9 times, and let's see, 64 over 2 is 32. Okay, so it looks like what you would get is you would get 9 times 32, and that would give the answer. Now, any of these kind of problems, you can check on your calculator. You know, just make sure you're right, okay? But that's the methodology that you want to learn how to do on a definite integral, is to do that. And what that represents is the area under that curve. That curve 9x is a line with a slope of 9. So that's how that goes. Okay, does that make sense? Get the antiderivative, then evaluate it. Okay, we're going to start pretty simple on these. Okay, this one right here, what is the antiderivative of e to the x? E to the x, okay, because the derivative of e to the x is e to the x. So what you do is you do e to the x, and you evaluate that from 0 to 1. First, do your antiderivative, then close it off. Okay, so all we got to do on this is plug in the 1, plug in the 0, and then subtract the result like that. Okay, so what you would get on this one is e minus what? Minus 1. Because anything to the 0 is 1, that's it. That's the exact answer of the problem. Okay, that would be the idea. Okay, all right, you guys follow that okay? I'm trying to start with real easy integrals. Okay, all right, next one. What is the antiderivative of 1 over x? ln of x. And you want to use absolute value. Get in the habit of doing that. So it's ln of x. Don't put the plus c. You only do that if it's an indefinite integral. If you were doing the integral of 1x dx without any limits, then the answer to that is ln x plus c. Anytime you do a definite integral, you're going to get a definite answer. Okay? So what we do is we evaluate that from 1 to 2. So that means what you're going to do is you're just going to do ln of 2 minus ln of 1. Okay, so you got your antiderivative. Now evaluate it by the fundamental theorem. ln of 2 is a decimal. If you don't know that, you could do that on your calculator and you just see a bunch of decimals popping up. Now, if you don't know what ln 1 is, a lot of times students don't know that. It's the same thing as log base e of 1, so it's 0 because e to the 0 is equal to 1. Okay, your calculator would bail you out of that, but I'd like people to know that the ln of 1 is 0 and how to figure it out in case you need to. So what you would get is this would be ln 2 minus 0. You don't need absolute value because 2 is positive anyway. So the area under that curve from 1 to 2 would be ln of 2, and that's exact. Okay, if you do that with a calculator, it's going to give you a decimal value, but I want the exact answer. Okay, so what I've done, in my opinion, are probably about as simple as it can get. Okay, these things right here are simple antiderivatives that don't take much work. Okay, what do you think? Okay, I'm going to put you to work on 2 of these then. Go ahead and try the next. Anybody got an answer on the first one? No. If you got something, be brave and call it out.
Decimal answer.
What'd you get?
25.556.
Oh, I don't want a decimal. I want the exact answer. Before you got that, what'd you get? 4e to the second minus 4. Or you could have it in a factored answer. You could have 4 parentheses, e squared minus 1. Okay, I'll show it here in a minute. Okay, anybody got anything on the second one yet? 2 ln 5, that's what I got. It's 2 ln 5. Okay, the antiderivatives on these are pretty simple. I'll put these up here and then we can take a look at them here. So what I did on the first one is I took the 4 out. That's a good starting point. The antiderivative of e to the x is e to the x. Okay, that's it. So then what you're doing from here is just bringing down the 4, then you're plugging in e to the second minus e to the 0. That's the fundamental theorem. That's how that goes like that. Okay, so your antiderivative is e to the x. 4 comes down. You're going to have e to the second minus e to the 0. E to the 0 is 1. So you could actually have either of these two answers. You can leave it in that factored form, or you can go there. Doesn't matter. They're both the same. But what we want typically is an exact answer. And you can go to your calculator and get a decimal approximation, but that's exact. Okay, does that look okay? Okay. Now what happens on the next one, what I did is I bring the 2 out. Okay, and then that's going to leave me with the integral from 1 to 5 of 1 over t dt. Okay, the antiderivative of 1 over t is ln t. Okay, and then that's going to be evaluated from 1 to 5. So once you get the antiderivative, it's pretty simple to finish. Just bring the 2 down, then you're doing ln 5 minus ln 1. Okay, the 2 is separate from that, so at the end you just multiply by 2. So ln 5, leave it alone. ln of 1 is 0, so there's your answer. Okay, does that make any sense? Give me a sign, some kind of signal, thumbs up, thumbs down, whatever, okay? Because I don't know. All right. Okay, let's finish. I think we're going to do this next page, and then we'll review for the test. I want to kind of get into use substitution with this also. And then we can finish the rest of this next week because I'll kind of get in the main ideas here. Okay, so these are going to require use substitution. And so what we're going to do on this, these integrals are not things that you can just do in your head like the last problems. So we need to look, first of all, let's just look at this integral. Don't even worry about the limits 1 to e. Let's just think about this. Let's think about how use substitution would go. Okay, this is not a simple basic integral, and you can't do the top and bottom separately. Okay, so I'll ask you, what do you think would be a good thing to set u equal to?
1 over t.
No, it wouldn't work. Okay, here's what you want to think of.
ln t.
When you do du, you're hoping you get what's left over. What did you say? ln t. Let's try ln t. Okay. All right, so what I'm going to do is that's going to be u. That's your u part right there. Okay, what's left over? 1 over t dt, right? What is the derivative of ln t? 1 over t dt. That's what we want. Okay, that's it. That's your u substitution. See, if you do it the wrong way, you're going to get stuck. So if you set it equal to 1 over t like you're thinking, you just get stuck. Even the derivative would be way different than what's left. Okay, so what we do is we're going to do that. Now let's put that integral together first of all. So what we have is that the ln of t gets replaced with u. Okay, the 1 over t dt, maybe some of you aren't seeing that. There's a 1 there, so it's 1 over t dt. That is du. Okay, so this thing right here I have in blue is going to become the du. Okay, so your integral is u du, which is easy to do. How do you do an integral of u to the first? Power rule. It's u to the second over 2. Now what we're going to do that's different is we're going to change the limits. You want to learn how to do this. Okay, so instead of plugging the 1 and e in, you don't do that because you change the variable. What you do is you take your u substitution which is ln t. Okay, and you start with that upper limit, which is an e, and you just plug it in, so you have ln of e. Okay, ln of e is equal to 1. The reason is because it really means log base e of e, that's equal to 1, because e to the first power is e. So that integral is, we're not going to put an e there, we're going to put a 1 there. Okay, so what happens is this thing changes to this thing. You got to change the limit just like you change the variables to u. Then you take the second limit, which is a 1, and you plug it in. You plug it into that u substitution, so you do ln of 1 like that. What's ln of 1? 0, so that changes. So I changed everything. So what I did is whenever you change these limits, all you ever have to do is just go there to whatever your u substitution is. You do ln of e, that gives 1. You do ln of 1, that gives 0. So you're changing it. Okay, so now what we do is we have a super easy integral that you can do to finish up the problem. So what you would do is the integral of u to the first is u to the second over 2, and then you're going to evaluate that from 0 to 1. But you got to change those limits. That's important. So what you would have now is you can go like this. You could go, and see that 1/2 could be factored out. The easiest way to do that is just bring that 1/2 out and then just do 1 squared minus 0 squared. Okay, just plug the upper limit in, plug the 1 in, plug the 0 in, subtract the result. So you're going to get 1/2 times 1 minus 0. So the answer to that is 1/2. And like any of these problems, you could graph ln t over t. And on your calculator, you could go from lower limit 1 to e. You have an e key on your calculator, and it'll give you 0.5. Okay, so you can be checked on the calculator. Okay, that's what you get into in u substitution on a definite integral. Okay, all right, let's see what we can do on this next one here. Okay, first thing I would recommend, what could you do with the 32? Take it out. Okay, if you have a constant multiplied, take it out. So you'll have 32 times the integral 0 to 1 of x times x squared plus 1 to the 7th times dx. Now, you know, talking about the test that you're going to have Thursday, the way I always do this for this level of a class is I tell you it's u substitution. And I have a blank for you to fill in u and a blank to fill in du. Okay, and then you got to do the rest of the problem. So any ideas about what would be a good u? Okay, let's try it. Remember, sometimes you just got to try it. So let's try to use x squared plus 1. Okay, now I'm going to highlight what's left over. We're hoping du will be what's in blue, or close. What is du? The derivative of x squared plus 1 is 2x, so it's 2x dx. That's close enough, right? You divide by 2. You want this to be x dx, so what you do is you just take this move, you divide both sides by 2. I'm going to write that as 1/2 when I do that, so now it matches. Okay, so what we're going to do is we're going to put this integral together as we go. We still have 32. Let's not worry about the limits yet. Times, okay, now how does this integral go? This thing in yellow is u, so that's u to the 7th, right? Okay, what is x dx? It's 1/2 du. And you can put it in like that if you want to, like that. Okay, so you got your u, and then the x dx was 1/2 du. Now, do you know how to do this integral? God, I hope so. What is it? Take the half out, u to the 8th over 8. Okay, now we're not ready to do that yet. But remember, when you do u substitution, you want to have an integral that's easy. Okay, what we got to do now is we got to change these limits. So let's go ahead and do this. The upper limit is 1. So what you do is you plug that into your u substitution. The u substitution is what I have in yellow, x squared plus 1. So you're going to just do 1 squared plus 1, so that's equal to 2. So that limit 1 changed to 2. Okay, now change the 0. You got to change both of them. So if you change the 0, you plug it into x squared plus 1. That's 0 squared plus 1. That's equal to 1. Now you've got a super easy integral to do from there. So again, what you do with those limits is plug them into whatever your u substitution is. Okay? Now, what you can do on this is you can bring the half out. That's a constant. So you'd have 32 times 1/2 integral 1 to 2 u to the 7th du like that. Okay? Now, from here, you would have 32 over 2 is 16. The antiderivative is what? U to the 8th over 8. And then you're going to evaluate that from 1 to 2. Now just use the bar to represent that. Well, notice 16 over 8 is 2. Now 2 is a constant, see. So you really have 2u to the 8th, 1 to 2. So you've got two choices. You can either do 2 times 2 to the 8th minus 2 times 1 to the 8th, or you can just kind of just write the 2 down and then do it like this. This is the way I do it. Just the 2, just kind of have it factored out. Then you would have 2 to the 8th minus 1 to the 8th like that. You could use your calculator to help. So 2 to the 8th is 256. 1 to the 8th is 1. So that would be 2 times 255. And then you'd have your exact answer. Your problem would be 510. That's it. Okay? Now it's the u substitution. Every time that any calculus teacher teaches u substitution, it's always challenging for students. But once you practice and do problems, you'll wrap your head around it and you'll start getting it down with ease. Seriously. I'm going to do one more, then that'll be our stopping point here for this, and we're going to talk about the test. Okay, so let's go to this next one here. We're going to have a line for u and a line for du. Now, when you have an e to a power in your integral, okay, you can pretty well bet that you want your integral to end up being e to the u. So what should I set u equal to in this problem? Negative x squared, exactly. We want to have e to, and that dx shouldn't be in the exponent. It should be down like that. I didn't type that right. Okay, so let's do that. Du is negative x squared. That way we'll have e to the u, easy integral. Okay, I'm going to highlight in blue what we're left with. Okay, tell me what du is. Negative 2x dx. What did we want it to be? X dx. What do we need to do to change it to x dx? There you go. Divide by negative 2. And I'm going to put a negative 1/2 there so that that cancels out. Okay, now I'm ready to do my substitution, see? Okay, so how does the integral grow? E to what? U. Negative x squared is u, right? Okay, what is this part in blue? X dx, what did it turn out to be? That thing. That thing right there. Okay, so that's going to be times negative 1/2 du. So that's your u substitution integral. Okay, everything is accounted for, and you have an integral that's easy to do, right? That's the thing. Now you got to work on your limits. Okay, let's start with the upper limits 1. What do you do with that 1? You plug it into the u substitution, right? The u substitution is negative x squared. So you're going to do negative of 1 squared. Now be careful. See, notice that negative is outside of the squaring. Okay, it's the negative of x squared. So that's going to be negative 1. So that means that upper limit is negative 1. We changed it. Okay, what do you do with the 0? Same thing. The 0 gets plugged into the u substitution. So that's negative 0 squared. What's that?
0.
Okay. Now don't worry about your limits being backwards. It doesn't make any difference. Okay? I mean, it's fine if it's that way. It doesn't make any difference. So this is the integral you're going to work out to get your final answer. So I would suggest that you take the constant out. That way you have negative 1/2 integral 0 to negative 1 of e to the u du like that. Okay? Now we're ready to roll. Okay, tell me what the antiderivative of e to the u is. It's e to the u. Why? Because the derivative of e to the u is e to the u. Okay, so that's going to give e to the u. Then you're going to evaluate that from 0 to negative 1. Okay? The way to do that is just write the constant down, plug in the top limit. Always do it in this order. So that's e to the negative 1. Plug in the bottom limit. So it's e to the 0 like that. Okay? Then work out what you can work out. Now, really what you would do on this is I would probably just say You can leave that e to the negative 1, or you could change it to 1 over e to the first, and then the e to the 0 is 1, and that's a good answer. You can multiply it out. You don't even really have to change the e to the negative 1. You can leave that e to the negative 1 if you want to, like there. That's it. Okay? So when you're doing this by use substitution, you got to change the limits too. If you don't, you're going to make the problem into an unnecessary mess. Okay? Okay, so let me close this off.